Salam alaikum tout le monde. Donc, nous sommes réunis cet après-midi pour assister à la soutenance de mademoiselle Bouعصيدة Eman. Donc, pour sa soutenance de doctorat, son sujet intitulé Smart Farming Solutions, Automated Crop and Plantation DCS. Donc, tout d'abord, je tiens à remercier les membres du jury qui ont réservé leur temps pour évaluer cette thèse. Donc, je commence par notre cher ami, frère, collègue, ancien collègue de l'université également, professeur Walloum de l'université de Constantine. Après, notre directeur de laboratoire et notre père spirituel de l'informatique de l'université également, le co-encadreur, professeur Hamid Siridi. Après, le directeur de thèse, professeur Farou Ibrahim. Et je termine par notre ami, frère Limi Khalid. Donc, vous avez 45 minutes à peu près pour présenter l'essentiel de notre travail. En passant après aux membres du jury. Bon courage.
Bismillah ar-Rahman ar-Rahim. Hello ladies and gentlemen, it's a great honor to be here today to present the work I have done during my PhD journey. First and foremost, I would like to express my sincere gratitude to the jury member for taking time to evaluate my work and for their valuable insight and feedback. I would also like to extend my thanks to the audience to be here on this day.
Les membres du jury sont fatigués déjà. Essayez d'aller doucement.
Today I will present my research titled Smart Farming Solution Automated Crop and Plantation Disease Detection, which address one of the major challenges in agriculture, plant disease. To give you an overview, my presentation will be divided in the following section. First, I will outline the importance of agriculture and discuss the critical issues of plant disease. Second, I will introduce the problematics by presenting the challenges and limitations found which our research aims to address. I will then outline the objectives of this research. After that, I will discuss the material employed. Next, I will present the contribution and the results, explaining the key findings of this research. Finally, I will conclude with conclusion and future perspectives. So, as we know, agriculture holds permanent significance as primary source for the global food security and as a vital economic sector in every country. Its development is necessary for meeting the demands of the growing population and also for generating profits for surplus production. However, the agricultural sector faces several threats that reduce product and disrupt the food supply chain and negatively impact the economies of the countries. Plant disease is one of the serious threats that affecting agriculture and resulting in several damages. According to the estimation of Food and Agriculture Organization of the United Nations (FAO), plant disease impose annually cost of 220 billion of the global economy. So early detection of the plant disease is necessary for combating them. One of the most efficient solutions for achieving early detection is automated plant disease detection, a key component of the smart farming, which is a modern agricultural practices that integrates modern technology such as artificial intelligence, remote sensing, and Internet of Things in agriculture. In the smart farming, automated plant disease detection involves deploying a sensor in the field to collect data and send them to the central unit. The central unit using artificial intelligence and data analysis techniques to analyze the data received from the field to detect the presence of the disease. Two main methods exist based on the type of data received. The first method involves analysis of environmental conditions and physiological changes in the plant associated with the disease emergence. The second method focuses in analyzing images of the crop and the plantation. However, the first method is considered ineffective due to its high cost, especially in large fields where an important number of sensors is required, while the second method is considered more cost-effective and scalable. On the other hand, the advance of the deep learning and its superior over other traditional machine learning and data analysis, it's become the most efficient solution for automated plant disease detection. This we can conclude that detecting plant disease from image using deep learning is the most efficient method in automated plant disease detection. Constantly, many models proposed to rely on deep learning, but they still face several challenges. The major challenges is the lack of data. Creating comprehensive data set including all types of plant and diseases is difficult due to the vast number of crop and disease species in the world. The second challenge is difficulty in capturing data because some diseases spread rapidly, making timely data collection difficult, and also in other cases where leaves infected with multi-disease, collecting data about all cases of this multi-infection, it could be impossible. Limited generalization occurs because the model becomes specialized to the type of crop and disease seen during the training. Because during the training process, the model not only influenced by the disease feature, but also influenced by the crop features. The proposed system is limited to detect a single disease from the leaf at a time, as they trained from data from a single disease infection, so it cannot be extended to detect a multi-disease infection. Another challenge is that most of the proposed systems are designed to detect diseases from the leaves. This can be explained by the fact that most of the diseases appeared first in the leaves. However, there is some diseases that not manifest on the leaves and affect other parts of the plant, such as branches. Now let's examine the core problematic stemming from these challenges, gives the challenges of limited data. How can we effectively address and overcome this limitation in developing robust disease detection models? What strategies can be employed to ensure accurate and generalized disease across different groups and disease types, including the detection of multi-disease simultaneously? So, the objectives of our research presented in detect the healthiness or infection of the leaves, regardless the specific crop or disease, detect multi-disease infection on the same leaf simultaneously, focusing on the most and well-known diseases in the leaves. Calculate the disease prevalence and assess the overall extent of the diseases to guide chemical spraying decisions. Detect diseases that affect plant branches without affecting the leaves. Two main datasets are employed as a material. The first dataset is Plant Village dataset, which is a public dataset containing more than 54,000 images of the group leaves divided in 38 classes. These images are captured under controlled laboratory conditions with uniform background. The second dataset is self-collected dataset of the apple branches infected with Nectaria cinebrina diseases collected from various online sources. This collection was driven by the absence of suitable dataset. It contained 500 images captured under real field conditions with non-uniform background. So the first contribution, it is a deep learning approach for cross-group and plant disease detection. To generalize the process of plant disease detection to all types of crop and diseases, we propose a deep learning-based system capable of organizing healthy and infected leaves across different crop types if the system not trained of them. The key idea is the focus on organizing the healthiness or infection of small leaf region without taking into consideration the type of the crop. The methodology employed to achieve this proposed system is presented in initial phase and introduced before the training phase. So the preparation of the new dataset phase consists from two main methods. The first method involves generalizing the disease detection process to any crop type by eliminating the influence of the crop features from the leaves. This can be achieved by splitting all leaves into small leaf regions that not contain any crop-specific features. So, we proposed to split each dataset images into a square budget of size 32 by 32 pixels. So the dataset images with the dimension 56 by 256 pixels are split in a metric of 8 by 8 patch, resulting in 64 patches. Some criteria are applied to the resulting patch to remove noise and retain only the relevant one. Patches with black pixel extending 15% are eliminated. These rush load were chosen to closely align with the characteristic of the blend village dataset, particularly the black pixel percentage of the original image, which is approximately 15%. The second method involves generalizing the disease detection process to any disease types by eliminating the focus on the disease-specific types and concentrating on organizing healthy and unhealthy patches. This can be achieved by labeling all the healthy patches extracted from all dataset images in healthy class and all unhealthy patches extracted from all diseased class as unhealthy class. In the end of this process, we will have a new dataset labeled in two classes. Healthy class H is equal to the sum from C equal 1 to the number of dataset classes of the sum of I equal 1 to the number of the image of the class C of the set of P such as P are healthy, and the unhealthy classes which is U equal to the set of the P such as P as unhealthy. In total, we will have dataset including more than 1,800,000 patches. So, the new dataset is used to train the CNN. We choose the smaller inception architecture, which is adapted version of the Google inception architecture for the small input size. These decisions are influenced by the success of the Google inception in plant disease detection. The smaller inception architecture consists mainly from three modules. The convolution modules consist from convolution layer followed by patch normalization and rule activation function. The inception modules receive the input from previous layer and apply to convolution layer and then match the result from the previous layer. The downsample module received input from previous layer and apply convolution modules and max pooling operation and then match the result from these two operations. After testing various parameter combination, we empirically choose the optimal one for the CNN as presented in the following table, and the data set is split into set: training set containing 80% and the testing set containing 20%. So the last step of the proposed system, it is the disease detection. So to detect the healthiness or infection of the test image, we propose to use the previous method. First, we split the leaf into small patch and then we eliminating the noise. And each patch is presented to classify it. So this process allows us to estimate the prevalence of the diseases from the leaves. So the prevalence rate of the diseases P equal to the number of the unhealthy patch PE multiplied by 100 divided by all the number of patches. The example test image in the slide, after the classification of the patch, the proposed system gives the disease extent, which is the test leaf is unhealthy with 28.13% of the leaves being affected. So now let's evaluate the result of the proposed system. As presented in the following table and image, the proposed system achieved an accuracy of 94.04 and loss function 0.1462. These results demonstrate the effectiveness of the proposed system. To identify the misclassification error made by the system, a careful analysis of the confusion metric are conducted. We found that the most of the error occurs in the healthy class due to similarity between certain disease symptoms and the natural characteristics of some group leaves, as presented in the figure. The first leaf is a healthy leaf, and the second was the affected one. And the most of the classification error occurs in a healthy class due to misclassifying patch with the smaller disease spots as presented in the figure. So, to demonstrate the generalizability of the proposed system, we tested it in a new dataset called plant disease symptom. From this dataset, we selected a new group type and affected with a new disease type that not seen during the training. The model achieved an accuracy of 97.22%, and the failure were observed from the same reason as those from the plant village dataset. The following table presents the comparison result of the proposed system with the state-of-the-art method. As we can see, the proposed system does not achieve the highest accuracy, but it demonstrated its robust performance and effectiveness. Unlike other state-of-the-art methods, the proposed system uses the entire plant village dataset, this ensuring broader applicability. And also the proposed system can detect any group type with any disease type. This makes it multi-group and multi-disease solution. And also can handle any new group and diseases type, unlike other state-of-the-art methods. The second contribution is a deep learning approach for simultaneous multi-disease detection on the same leaf. To detect multi-disease from the same leaf simultaneously at the same time, we proposed a deep learning system capable of recognizing the multi-disease from the leaves of any group type, even if the system not trained of them. The key idea is recognizing each disease symptom separately from small leaf region without taking into consideration to the disease stop. This can be achieved by using a new proposed method named isolation method. The isolation method involves isolate each disease symptom separately from other disease symptoms and from the group types. This can be achieved using the same method from our initial contribution. Each image is divided in 64 patches with 32 by 32 pixels. And then we remove noise from the patch with black pixel extending 50% are eliminated. For the resulting patches are labeled as follows. All the healthy patch extracted from all image dataset are labeled as healthy class, and all unhealthy patches extracted from and each unhealthy patches are labeled with the disease it represents. As we can see, we have two images, one from black root apple class and the second from grape black root class. All the unhealthy patches extracted from both images are labeled as black root patches. So in the end, we will have dataset labeled into 21 classes, one healthy class, each equal to the sum from C equal 1 to the number of dataset classes of the sum of I equal 1 to the number of the image in the class C of the set of pH such P is healthy. And for each unhealthy class affected with the diseases D equal to the sum from C equal 1 to the number of the dataset classes from the sum of E equal 1 to the number of image in class C of the set of the PD such as P is affected with the diseases D. So, as we can see, the dataset presented a challenge of imbalance. We have big difference between classes. We have the major class, healthy class, and minor class, mosaic virus class. This imbalance can create a problem during the training process, as the model can be biased toward the major class and resulting in lower accuracy for the minor class. We selected the smaller acceptor architecture as CNR architecture for our proposed system, and we selected another CNR architecture, mini VGGNet and Net5 to perform a comparative experiment. And after testing various hyperparameter combination, we empirically chose the optimal one for each model as presented in the following table. The last step of the proposed system is the multi-disease detection. To detect the multi-disease from the test leaf, we proposed to use the same method as our initial contribution, we split the image in the patch and we eliminate the noise, and after that the CNN classifies the patch. So this system allows us to estimate the disease prevalence rate of each disease separately, and also estimate the overall disease extent, which equal to the sum of all diseases prevalence rate presented in the leaf. For the example test image, due to the lack of data set, we couldn't find the leaves infected with mildew disease. For that, we perform our test on leaves infected with only one disease, which is north leaf blight disease. So the proposed system gives the north leaf blight prevalence rate plus the disease's extent, which equal to the prevalence rate, because the diseases are infected only with a single disease. So the result of the comparison experiments demonstrated the effectiveness of the smaller inception over other CNN architects. It achieved the highest accuracy, which is 90.57, and the lowest loss, which is 0.2954. And to address the challenge of imbalance, we use the class-wide to balance the training process. This adjustment improves the accuracy of the minor class as presented in the table, and reduce the bias toward the major class. As we can see from the confusion matrix, we see the reduction in the misclassification error to the healthy class. To identify the misclassification error for the proposed system, careful analysis of the confusion metric are conducted. We found that most of the errors occurs in classifying patch with smaller disease spot, and differentiate between some disease symptoms as presented in the figure, and also distinguish a healthy patch from this containing yellow sign due to some disease. The third contribution is an intelligent system for detecting diseases in upper three branches. So to detect diseases from upper branches, we proposed an intelligent system based on advanced machine learning techniques and image analysis and data pre-processing. And as presented in the slide, the proposed system consists mainly from 4 steps. The first step is the acquisition step. This step involves capturing RGB image from the field using smartphone or fixed camera on the surveillance drone. The second step is a pre-processing step. In this step, many operations are applied to each image to improve the quality and extract the important information. The first operation is the conversion of the color space from RGB to lab channel to extract important color features. The second step is contrast enhancement using a CLAH method to improve the quality. After that, noise reduction using medium filtering and trash load and morphological operation. The trash load is used to create a binary image of the disease spot, and morphological operation is used to improve the detection quality. And finally, byte-by-byte operations are performed between the original image and the binary image to create the masked image. The third step of the proposed system is the GMM training. First, we initialize the GMM with 2 questions. One present the disease spot and other present the healthy part. The probability distribution of each pixel is calculated based on the color intensity of the lab channels. And the K-means approximation algorithm is used to update a parameter during the training process. The final step is the disease segmentation. In this step, we created the segmentation mask based on the result of the GMM. Each pixel with high white means they frequently appear, and with low variance means their color stay constant, are presenting the disease spot. And finally, the masks are applied to the original image using a logical AND to segment the disease spot. As presented in the following table, the proposed system segments the disease closely aligned with the ground truth disease spot for all the test images. The classification challenges are observed in segmenting image with dense variation, and means the system detects some healthy part as a disease spot because they have a color similar to the disease spot. So, in this thesis, artificial intelligence techniques are employed to detect diseases from crops and plantation. The proposed system demonstrates strong performance and showing their potential for broader applicability and contributing the global food security initiatives. The future research aims to enhance the system performance by improving the adaptability in the environmental conditions and improve the accuracy of the proposed system, and also using the sliding window approach for better patch generation.